Work. So now we're switching into energy, and we're going to get into our first part of energy, which is work. And let me describe the thinking about this and the thought process behind this. First, energy. Well, we kind of have a circular definition. So energy is what it is, but we can put energy in different places. So we can store it, and it's a good way to think of it. It's like money. I can put it into a bank account, or I can put it into my college education, or I can put it under my mattress. Right? You get to decide. Some of these we're going to have. So different places that we can put energy. We can have kinetic energy. We use K for that. We can have thermal energy. So this is less useful for us, but something that we may have to keep track of. This is the motion of atoms or particles. We'll have gravitational potential energy. Notice we're using U to indicate potential energy. We'll have elastic potential energy. So if there's a spring involved, for instance. And we'll have electrical potential energy, get to the second semester, and then finally we'll get to magnetic potential energy. So notice the potential energies all are U's, and kinetic energies are K's. We're going to have a couple different flavors of kinetic energy, but we'll get into that when we get into rotation. The key thing is, though, we're going to be shuffling things back and forth. So we can shuffle from kinetic energy to potential energy, right? So if I roll a ball up, if I push a ball and it rolls up a hill, then I'm converting that ball's kinetic energy into potential energy. But how did that start? That started with me pushing, right? So the way that we get energy into or out of a system is what we're going to worry about now. So what we do is we do work on something. So our definition of energy is the ability to do work, and work is how we get energy into a system. I know it's kind of circular, but just go with it. So we work by applying a force over some distance, and that allows. So you're going to push on the back of your car to get it to move when you run out of gas, and the longer you push it, the more energy you're putting into it. So we'll get into work, some calculations of work. We can also transfer energy by heating. So if something's hot, something's cold, right? Some of that kinetic energy of motion of the atoms is going to transfer from one to another. And we can also have radiating. We're not going to worry about these last two. So for us, the only way that we're going to worry about getting energy into or out of a system is through work. So application of a force over some distance. So this is our definition. So we're going to say work is equal to force times distance. This is a physics definition. Work is not a vector quantity. So notice that force and displacement are both vector quantities. Talk about that in just a minute. But work itself is not a vector quantity. It's just a number. So energy doesn't have direction, right? So if you have a ball of energy, right, it's just there. It's not moving in any direction. As a reminder, our SI unit is going to be the joule. It's also the same as a Newton meter, which is also the same as kilogram meter squared per second squared. All means the same thing. We have to be careful. So Newton meter will show up again when we get to torque. So this is a Newton meter. It's going to show, anyway, it's going to be a little bit different. So what are we doing? So really we're multiplying two vectors. Notice the small arrow over the force and the small arrow over displacement. So this means I'm going to have two vectors and I'm multiplying them together. There are two ways that we'll do multiplication of vectors. So one way is where we're interested in those that are in the same direction. So notice that my force is in the same direction as displacement, right? So this is going to be the dot product. So we'll use, the dot product tells us how much those two vectors overlap. It's sort of like a projection. Well, it is a projecting. So we'll get to a cross product later. So when we're worried about things, how much they don't overlap, so how much they're orthogonal to each other. But we're not going to worry about that right now. So importantly, though, this is a cross product. We're multiplying two vectors together, and we get a scalar out. So we get a number, and that number is a joule, named after this dude. All right, a brief comment about the joule. So a pretty small value. So here are some examples. Mount St. Helens eruption was about 10 to the 18th joules. Yeah, kind of hard to get your head around. Daily human intake of food. So you take in about, 2,000 calories or 2 million chemistry calories. A day to keep yourself going. That's about 10 to the 7th joules. A human heartbeat is about half a joule. Didn't know that. A hop of a flea or breaking a bond of DNA, really tiny, small amount of joules. So we'll end up with large numbers for joules for things that we're doing. But joule is the unit that we'll use here. So in chemistry, you might have used calories, which is related to joules. But say here we're going to use joules for energy in physics. And the most important thing, so you have a concept of work, right? So you go to the gym and you I don't know, you run in place and you sweat, but you haven't done any work. So if you're holding a book in the air, I encourage you to try this. If you hold a book there stationary, right, you're applying a force, but it's not going anywhere, right? So you'll get tired and you may start sweating, but that book is not having any displacement. It's not having any motion. So it is not, you're not doing any work. Sorry, physics doesn't care. If you lift a box, you're doing work. If you carry it across the room, you're not doing work, right? Because you're lifting against gravity, which is perpendicular to the direction of your motion. So that's not going to give you any work. And then you can multiply things together again. So the key thing is that we're finding the amount that these two vectors overlap, right? And there's a shortcut for this, and the shortcut of this is to take the cosine. So one equation that we'll have for work is that it's equal to FD to the force times displacement, or force times distance times the cosine of the angle between the two, right? So that tells you how much they're overlapping. So if you're applying a force like down, like the lawnmower guy, some of that force you're pushing the mower into the ground, that doesn't count as work because it's not moving into the ground. Some of that force that you're applying is pushing it forward. It's that part that's pushing it forward that matters, and that's going to be putting work into the mower. The rest of it is just wasted. You're making frictional and heat, which we don't care about. Notice the lady's lifting up the bag so that she's applying a force in the vertical direction, but when she walks, right, that force that she's applying on the bag is in the vertical direction, and her displacement's in the horizontal direction, and that is not going to give any work. Sorry, you may get tired carrying it around, but that's not work. Okay, sign of work really matters. So far we've had a sign which indicates a direction on our axis symbol, but work has a sign, but it's not a vector, so that means something. And technically I can't have negative energy, right? That doesn't make sense. Well, maybe if you get into dark matter and things, but for this class, we won't have a negative energy, but we can have a negative sign for work. And what that means is it means how much energy is either going into positive or coming out of negative from my system that I'm interested in. So look at these three examples here. So I'm going to have this first one where my force has a component that's in the same direction as displacement, right? So I'm adding energy into it, right? If I'm pushing a ball, that's going to be going faster and faster, right? It's going to be gaining energy. If my force is perpendicular, it's zero, so nothing's going to happen. And if my force is in the opposite direction of displacement, right, so I'm slowing it down. So I'm adding energy in the, I'm doing work in the opposite direction of displacement, right? So that means something's got to be moving, and I'm applying a force in the opposite direction, and it must be slowing down. I'm taking energy out. So key things that the sign in work tells you if you're adding energy into the system that you're looking at, or you're taking it out of the system that you're interested in. So key thing, work is a scalar, but it has a sign, and the sign tells us which direction the energy is going. Okay, let me think about this. So the sign of work for these positing for the following instances. Pause the video and give these a try yourself. 3, 2, 1. Okay, car speeding up. I'm adding energy into that, so the sign of work is going to be positive. Car slowing down, I'm taking energy out of that, so my sign of work is going to be negative. I must apply force against the direction of displacement. And finally, I have a rocket taking off, and that must be adding energy into it, so it's positive work. And skydiving at terminal velocity, 0 net force, so I'm neither taking energy into it or taking it out of it. There's no work being done. Anyway, I hope this is helpful. We'll get into a few more things in just a minute. Talk to you later. Bye.